Hello. In this video, I'm going to go through graphs of uniform acceleration motion. I also show you some of the mathematical models that are connected to these graphs. Here we have a series of points in a displacement time graph. And when we have uniform acceleration motion, line of best fit through the points is parabola opening upwards or downwards depending on the direction of acceleration. And now we have parabola opening upwards, and here is the equation for our line of best fit, and we can see it's a parabola opening upwards. And let's make this a little bit simpler and saying that these two terms here are zero. They are really close to zero. So we could say that this model is y equal 0.49 x squared. However, we don't have x on a horizontal axis in this question in physics. We have time there. So if I change this mathematical model into the form of replacing this gx with displacement x and changing this variable x here to time, our model is x equals 0.49 time squared. And if you compare that to the mathematical model of uniform acceleration, where we have s equal half times at squared or x equal half times at squared, you can actually see that this term here, this 0.49, is half times acceleration. So in this measurement, acceleration is 0.49 times 2, that's close to 1. Then what we can get from this graph, other than we could calculate acceleration, we can actually find values of velocity. And this is really important. When you have displacement time graph, we can find values of velocity using gradients of tangent. And I will add a point here on my graph, and I will also add tangent line through that point that I can be moving. And we can also see the equation for the tangent line over here. And what we are interested in is gradient for this tangent line. And if you remember how gradient is calculated, it's the change in vertical axis divided with change in horizontal axis. And if we look at the quantities here, we have displacement on vertical and time on horizontal. So gradient in this case, in this graph, will give me displacement divided with time. And yes, that's velocity. So gradient of this tangent line is giving me instantaneous velocity values wherever I move this point and also tangent line. And we can actually see that if I start moving this point, we can see that this value for gradient here is increasing, which is of course the case when we have uniform acceleration motion. That's what happens. Velocity should increase. And as we go further and further, we can see the gradient for the tangent line is increasing more. And that's how we get velocity values from displacement time graph. Now, let's do velocity graph from this displacement time graph. And the way we will do it, I will take values of gradient of this tangent line at some points. So if I start from 0, we will get the velocity being close to 0, 0.05. Then I at 2 seconds, my velocity is 2.03. At 4 seconds, velocity is 3.98. At 6 seconds, 5.99. And then at 8 seconds, we have 7.94 for our velocity value. And then if I go a little bit further at 10 seconds over here, our velocity is 9.92. And those values we can use to make velocity time graph. And let's see that next. And here is our velocity time graph. And we can see that these points are lining a straight line. So if I add a line of best fit, it is actually straight line going through the origin, implying that our measurement or our object was starting at rest and our velocity is increasing steadily, meaning we have a uniform acceleration. Now, this gradient value over here for the line of best fit, this will give us acceleration. And if, again, we compare this to the mathematical model of velocity in uniform acceleration motion, we can see that we have time on the horizontal and we have velocity on the vertical. So if I use this mathematical model from GeoGebra, again, I can say that the 0.05, we can say this is 0. So let's focus on this first part of the model. And if I replace this gx with whatever I have on the vertical axis, that's v, and x I replace whatever I have on the horizontal axis, our model is v equals constant times time. And now the constant is acceleration. So again, we can see the connection between mathematical model and graph. So equation for that straight line is v equal at. And we get the same acceleration value as we got from the displacement time graph. It's roughly 1 meters per second squared. Then final graph is acceleration graph in uniform acceleration motion. Let's look at that next. And here is our acceleration as a function of time graph. And we can see we have a horizontal line, meaning our acceleration is constant. Then let's look what else we can get from these previous graphs. So first we were looking what do we get by calculating values of gradient. We go from displacement to velocity and then from velocity to acceleration by finding values of gradient. But now, how about if we calculate areas underneath the graph and see what we can get? Now here we have an acceleration as a function of time. And if we think, what do we get by calculating area underneath this straight line? If I think about this one square in the middle here, and if I would think, how do I calculate area for that square? Well, we will calculate it by width times height. Now the width of this square is time, height of this square is acceleration. And if we think, what do we get by calculating acceleration times time? And yes, it's velocity. To be more precise, we will get the change in velocity by finding the area underneath this graph when we have acceleration on the vertical axis. And if we calculate this area quickly, we can see that, well, height of the rectangle is 1. And if I go to 10 seconds here, 1 times 10 seconds is 10 meters per second, or value for this area is 10, and it's the change in velocity. So velocity change 10 meters per second when time goes from 0 to 10, and we get that by calculating physical area underneath this graph. Then going back to velocity time graph, and from this graph, if we calculate area underneath this straight line, again, we look, what do we have on vertical axis? What do we have on horizontal axis? So area underneath this straight line in this graph is velocity times time, and that will give us displacement. And if we look at this area underneath this straight line, it's forming a right-angled triangle, and formula for right-angled triangle is half times base times height. So half times velocity times time, that's how we get area underneath this straight line. Now, if I change velocity, knowing that we have uniform acceleration, velocity to be a times t, our area calculation becomes half times a t squared. And again, that's a formula you can find from formula booklet or data booklet, and that's the distance calculation in uniform acceleration motion, half times at squared. So finding the physical area underneath this graph on a velocity time graph, we will get change in displacement. And that's really key for motion graphs, that if we go from displacement to velocity to acceleration, we go that by finding values of gradient. And then if we go back from there, from acceleration to velocity and from velocity to displacement, we will do that by finding the area underneath the curve. And it really doesn't matter whether we or not we have a uniform acceleration motion. This method works all types of motion. And that's really a key in motion graphs when you face those. But here was graphs of uniform acceleration. See you in the next video.